Hello there, and welcome back to Cosmic Whispers. It's a quiet night, perhaps. Maybe you're listening to this on a walk, or as you're settling in for the evening. Have you ever looked up into that vast, dark expanse and felt a sense of stillness? A profound, almost eternal quiet? What if I were to tell you that this peace is an illusion? What if the space we inhabit, the seemingly empty void our small blue world drifts through, is not quiet at all? What if, instead, it is the echo chamber of an ancient and almost unimaginable violence? Let's try a thought experiment. Imagine just for a moment the sky tearing open. Not with a single flash, but with a cascade of light. Not one explosion, but 15, all erupting in terrifying succession, in the same celestial neighborhood, relatively close to one another in both space and time. It's the kind of cataclysm we expect to read about, a headline from a distant galaxy, an event observed safely from billions of light years away. But what if we aren't the observers? What if I told you that right now, our entire solar system, you, me, and the Earth beneath our feet are passengers, sailing directly through the very heart of that ancient aftermath? This isn't a what-if scenario. This is our reality. This is our home. Welcome to the local hot bubble. When a cluster of around 15 massive stars reaches the end of its life in spectacular, concussive fashion, it does more than just make a bang. It fundamentally re-engineers the cosmos around it. Such a violent series of events, occurring over a span of just a few million years, becomes a cosmic sculptor, a force of both destruction and creation. The combined power of those sequential blasts acted like a colossal cosmic broom. The forces unleashed by the supernova were so immense that they swept aside the thin, cold interstellar dust and gas that once filled this region. A monumental void was carved out, a cavity of incredibly low-density matter. But this was not a gentle clearing. It was a violent scouring, an act that pushed all that material outwards, compressing it into a single, ever-expanding shock wave. That shock wave, that wall of displaced matter, continues to hurtle across our galaxy to this day, expanding at a rate of approximately 6 kilometers every second. And in its wake, what was left behind? Not emptiness, but something arguably stranger. The region was filled with a ghost, a tenuous, invisible plasma, superheated by the explosions to a staggering 1 million degrees Celsius. This simultaneous Swiss cheesing and superheating of the interstellar medium is what astronomers now call a hot bubble. It is a structure born from the end of stars, but as we will see, it is also a structure that becomes a cradle for their beginning. The most unsettling part of this story, as I mentioned, is that this is not some distant structure lurking in a faraway corner of the universe. Our solar system isn't even just approaching it. We are already deep inside it. We have been for millions of years. We are, at this very moment, charging headfirst towards its point of origin, blissfully unaware of the raging furnace that once defined this space. This is the local environment that exists around our solar system. It is our cosmic neighborhood, and it's a neighborhood we are only just beginning to truly explore and understand. But with every passing year, and with every new instrument we point at the sky, its nature is becoming clearer and clearer. So what do we truly know about this local hot bubble? How precisely did it form? How did we even discover we were in it? And what more is there to be discovered in this invisible, superheated ghost? I'm Alex McCone, and you are listening to Cosmic Whispers. Join me today as we walk through the extraordinary aftermath of exploding stars and discuss how scientists even determined we were in the heart of a cataclysm to begin with. The local hot bubble was not always something we knew about. For most of human history, space was just space, a dark, cold vacuum. The revelation that we were inside a specific, defined, and hot structure came slowly, born from a technological mystery. It all began in the 1970s. As our ability to see the universe in new wavelengths of light expanded, astronomers launched rockets and satellites capable of detecting X-rays. They expected to see X-rays coming from specific high-energy objects, black holes, neutron stars, or distant active galaxies. And they did. But they also found something deeply puzzling. No matter where they pointed their X-ray telescopes, they detected a faint, diffuse, low-energy X-ray emission. It wasn't coming from a single point. It was coming from everywhere. The entire sky was aglow with a soft X-ray fog. What could possibly cause this? The leading hypothesis was evocative. Scientists proposed that this glow was the signature of a vast, local cavity in the interstellar medium. They called it a superbubble, and they theorized it was filled with that exact kind of tenuous, million-degree, low-density gas. At such extreme temperatures, this thin plasma would indeed glow, emitting the very low-energy X-rays that our new telescopes were detecting. It was a beautiful, elegant explanation. But in science, an elegant explanation is rarely enough. Doubt soon followed. In the 1990s, another discovery complicated the picture. Scientists found that X-ray emissions could also be generated much, much closer to home. They could happen anywhere that neutral atoms from the interstellar medium, like hydrogen, interacted with our own solar wind, the stream of charged particles flowing from the sun. This interaction, a process called charge exchange, also produces a soft X-ray fog. Suddenly, the bubble hypothesis was in trouble. Were we seeing the glow of a million-degree superbubble? Or were we just seeing the weather of our own solar system? The data was ambiguous. The all-sky glow might not be a map of a giant bubble after all. It might just be a local phenomenon, a veil draped over our own cosmic backyard. For decades, the question remained. How do you separate the foreground from the background? How do you know if the fog is in the yard or if it fills the entire city? The answer came, as it so often does, with a clever new mission. In 2014, NASA launched a brief but brilliant rocket experiment. Its name was the Diffuse X-ray Emission from the Local Galaxy Mission, or DXL. DXL's mission was simple: to measure the X-ray fog with precision. It flew above the part of our atmosphere that absorbs these X-rays and pointed its detectors at the sky. Its goal was to separate the two competing sources. And it succeeded beautifully. The DXL mission found that, yes, some of the fog was coming from within our solar system. It confirmed that the solar-wind interaction was real. But it also found that this local source could only account for about 40% of the total low-energy X-rays detected. This was the smoking gun. The other 60%, the dominant source, had to be coming from outside our solar system. The DXL mission affirmed that the primary source of the glow was exactly what had been hypothesized decades earlier: a vast, diffuse, million-degree region of interstellar plasma. The local hot bubble was real. This confirmation was a triumph. But it also opened the door to even deeper questions. The what had been confirmed, but what about the why? What could possibly create such a massive, energetic void? And what could explain the thousands of young newborn stars that, astronomers noticed, seemed to surround this void like a string of pearls? The prevailing answer, when it finally came together, proved to be both astonishingly violent and utterly fascinating. The evidence suggests that our local hot bubble is the direct aftermath of those 15 or so supernova explosions. This wasn't a single, simultaneous blast, but a sequential drumbeat of death, a series of massive stellar explosions erupting in relatively close proximity to one another over a span of several million years. From all the available data, scientists have been able to wind back the clock. They estimate that the first of these massive stars went supernova roughly 14 million years ago. Each explosion, as it occurred, expelled an enormous, incomprehensible amount of energy. Each blast sent out a new shockwave, reinforcing the ones that came before it, pushing out the surrounding interstellar material, sweeping the region clean, and heating the remaining gas to those extreme temperatures. It's a fantastic story. But how, after 14 million years, Could we possibly know this? How does an event so ancient, so distant, leave a fingerprint here on Earth? The answer, incredibly, lies buried at the bottom of our deepest oceans. Evidence for these ancient nearby explosions has been preserved in our planet's own geological record. In deep-sea sediment deposits and crust samples, scientists have found a very special radioactive isotope of iron called iron-60. Now, iron-60 is special for several reasons. First, it can come from a few different sources, but the most common and significant source of it in our galaxy is believed to be the fiery heart of massive supernova explosions. It is forged in that final cataclysmic moment and then blasted out into the cosmos along with all the other elements. Second, and most crucially, we know this iron-60 is extraterrestrial. Our Earth, in its normal geological processes, has no way of producing iron-60 on its own. So, when we find a layer of it in the seabed, we know it must have rained down from space. This has even been confirmed by matching deposits found on the Moon, which has no atmosphere to burn up or deflect this cosmic fallout. But the real magic of iron-60 is that it acts as an elemental clock. Like all radioactive isotopes, iron-60 decays over time. We know its half-life, the time it takes for half of a given sample to decay. For iron-60, that half-life is 2.6 million years. It decays into another radioactive isotope, cobalt-60, which itself has a very short half-life of just 5.3 years, before it finally decays into a stable element, nickel-60. Because of this predictable multi-stage decay, a deposit of this material acts like a radioactive hourglass. When scientists find a deposit, they can compare the amounts of iron-60, cobalt-60, and nickel-60. This ratio, this elemental signature, reveals with remarkable precision when that material was deposited on our planet. And luckily for us, over the last couple of decades, international research teams have found several such deposits. In 2016, a breakthrough came. Iron-60 deposits were found in deep-sea crust samples taken from across the globe from the Pacific, the Indian, and the Atlantic Oceans. The data was global, and it was clear. The samples showed two distinct spikes in this radioactive debris, pointing to at least two major periods of supernova activity in our not-so-distant past and not too far from our solar system, within about 326 light-years. The geological record showed a spike of iron-60 between 3.2 and 1.7 million years ago, and it showed another, older spike between 6.5 and 8.7 million years ago. Nuclear physicist Anton Wallner, who led one of the research teams studying these deposits, noted that the fact the more recent debris was spread across 1.5 million years was incredibly telling. It strongly suggests that this wasn't a single event. It was, as he put it, a series of supernovae, occurring one after another in close succession. An astrophysicist named Dieter Breitfurt, who led a second team, even identified a likely source for these explosions, which would have occurred between 196 and 423 light-years from our Sun. The supernova that created our local hot bubble, they proposed, were likely part of an aging star cluster. The surviving non-exploded members of this cluster are still with us today, now known as the Scorpius-Centaurus stellar group. Using the precise clock of the iron-60 deposits, the teams were able to trace the signals of specific explosions. They could point to one supernova that happened 1.5 million years ago, and another at 2.3 million years ago. They could even estimate the size of the stars that died. They were the result of the deaths of stars that were 8.8 times and 9.2 times the mass of our Sun, respectively. This isn't just a hypothesis anymore. This is history, written in radioactive ink, buried on the ocean floor. The story doesn't end 1.5 million years ago. In fact, the local hot bubble is not a static relic. It is still growing today, albeit much more slowly than when the supernova first exploded. The speed of its expansion has plateaued as we noted, at about 6 kilometers per second. But its most profound impact is not its expansion, but its role as a creator. This is where the story shifts from cosmic destruction to cosmic creation. In 2022, astrophysicist Catherine Zucker authored a groundbreaking paper that, for the first time, reconstructed the complete evolution of our galactic neighborhood. Her team traced the intricate chain of events that first created our local hot bubble, and then, crucially, led to the formation of all the young stars we see nearby today. To do this, they used data from one of the most revolutionary tools in modern astronomy, the European Space Agency's Gaia telescope. Think of Gaia as the ultimate celestial mapmaker. It is in space, meticulously charting the precise 3D positions and 3D motions of billions of stars in our galaxy. Zucker and her team used this incredible data to create not just a 3D map, but a 3D space-time map. They could rewind the galaxy. By tracing the positions and motions of all the stellar clusters near us, they rewound 20 million years of star formation history. And when they did, they made an incredible discovery. The implications were clear, and they were breathtaking. Within 500 light-years of our planet, all of the young stars and all of the known star-forming regions reside on the surface of our local hot bubble. Let that sink in for a moment. They are not scattered randomly. They are not inside the bubble with us. They are on its edge. The picture that emerged was this. The bubble, as it expanded, acted like a cosmic snowplow. The shock wave pushed and swept up all the loose gas and dust it encountered. This material, compressed and piled up along the bubble's outer edge, became denser and denser. Eventually, this compressed gas, under its own gravity, began to collapse. And in those collapsing clouds, new stars were born. The local hot bubble is a stellar nursery. The very act of destruction that cleared this vast cavity is the same act that is now triggering a new wave of star birth all around us. The death of one generation of stars is literally building the next. We are learning more about these stellar nurseries all the time, particularly as new images are taken by our telescopes. Here, for example, is a spectacular image of the Chameleon 1 dark cloud. This is one of our nearest stellar nurseries, captured by the Dark Energy Camera on the Victor M. Blanco 4-meter telescope in Chile. By studying the starlight propagating from within these dark, dusty clouds, scientists can tease out the details of how stars form, which helps us better understand the bubble's ongoing impact. You might not have seen this particular image before, as new space news is emerging constantly. It's a topic I've actually talked about in my newsletter, which I've recently launched to help us all keep up with the breathtaking photos and the new breakthroughs that reshape our understanding of the cosmos. If that sparks your curiosity, you can sign up to never miss the most exciting news by following the link in the description below. From the bubble's birth 14 million years ago, Zucker and her colleagues were able to identify 4 distinct epochs of star formation on its shell. It began even before the bubble, about 16 million years ago, with the birth of the Upper Centaurus lupus, UCL, and Lower Centaurus crux, LCC, star clusters. These were the very stellar populations that, about 14 million years ago, were the source of the first stars that went supernova to create the bubble. Then, the bubble's own creative work began. Epoch 1, about 10 million years ago, the bubble's first children were born. The Upper Scorpius Association and older stars in that region were formed. Epoch 2, about 6 million years ago, the expansion continued, triggering the formation of the Corona Australis cluster and the older stars in the Taurus cloud. Epoch 3, around 2 million years ago, the stars in the Lupus and Chameleon clouds, like the one we just saw, as well as younger populations in Taurus, came to be. Epoch 4, the present. We are living in the 4th epoch. We can observe the dense, star-forming molecular gas that surrounds the LHB right now, which will, inevitably, lead to even more star clusters being born along the bubble's outer edge. With all of this stellar creation happening because of the bubble, you might be surprised to learn that we, our sun, our solar system, are interlopers. Our sun did not form inside this bubble. It wasn't born from its shell. In fact, our sun was about 978 light-years away when the first supernova went off. For billions of years, our sun was a distant witness, following its own path through the galaxy. It was only about 5 million years ago that the sun's galactic orbit, by pure chance, took it into the bubble. We drifted across the boundary and into this ancient, hot, and empty cavity. And now, just by coincidence, our sun happens to be located very near the center of the LHB, drifting peacefully in the heart of what was once a raging furnace. At this point, you might be wondering, why are we so calm? If we are inside a bubble where the plasma temperatures can reach 1 million degrees Celsius, shouldn't we be, well, vaporized? Have you ever wondered about that? How we can coexist with such an extreme environment? The key, thankfully, lies in that plasma's density. The 3D maps from Zucker's 2022 publication show our local hot bubble in a dark, empty blue. The density inside our bubble is extraordinarily low. It contains about 100 times less hydrogen than the typical average interstellar medium. So, while the temperature of this gas is immense, meaning the few particles that are moving incredibly fast, there are simply too few of them to transfer any meaningful heat to us. It's the difference between being hit by a single, fast-moving, but tiny speck of dust and being submerged in boiling water. The first is imperceptible. The second is fatal. We are protected by the sheer emptiness of our bubble. Tracking these temperatures has provided even more evidence of the bubble's existence and its intricate structure. The eRosita X-ray telescope, part of the joint Russian and German Spectrum-Röntgen Gamma (SRG) mission, has gathered the most detailed all-sky survey of soft X-rays to date. Launched in 2019, data from eRosita has allowed a team of scientists, led by the Max Planck Institute for Extraterrestrial Physics, to create an even more detailed 3D map of the LHB. This map was so precise, it even identified a temperature gradient. The galactic south pole of the bubble was slightly hotter than the galactic north pole. This temperature difference could be explained by more recent supernova explosions in the south, still echoing through the plasma. By creating this bubble map, the team also found that the LHB is not a perfect sphere. It's stretched out, almost like an hourglass, elongated towards the poles of the galactic hemisphere. This shape makes perfect sense. The hot gas in the bubble expands in the direction of least resistance. It's much harder to push sideways against the dense, star-filled disk of the Milky Way, so the bubble has expanded up and down, away from the galactic disk. With this new data, a new picture of our galactic neighborhood is emerging. Our local hot bubble looks like a three-dimensional splatter, and it's surrounded by, and even overlapping with, other galactic structures. We see the Gum Nebula, another known supernova remnant, shown in red. We see dense molecular clouds, the very walls of our bubble, in orange. This new map suggests that our Swiss cheese galaxy, as some astronomers call it, is likely common. The Milky Way may be filled with these cavities, all blasted out by gigantic supernova explosions, with new stars forming along the edges of the holes. And like Swiss cheese, it appears that some of these superbubbles may have tunnels connecting them. The 3D maps suggest our local hot bubble could be part of an intricate network of similar features. For example, astronomers have identified what they call the Canis Majoris Tunnel, which seems to connect our local hot bubble to the aforementioned Gum Nebula, another larger superbubble. The map also revealed another, previously unknown interstellar tunnel, stretching towards the constellation Centaurus, possibly connecting our bubble to the neighboring Loop I superbubble. While these interstellar tunnels are tantalizing, our current understanding of them is limited. But the very idea is awe-inspiring. These tunnels of hot gas, these bubbles of star formation, all shaped by the death of gigantic older stars, it paints a picture of a galaxy that is powerful, interconnected, and constantly evolving. It suggests that stars are not just born and die in isolation. Their energetic output continues to mold the environment for millions of years after their demise. And as our observational tools become more sophisticated, we are beginning to uncover the true extent of these hidden, grand structures. So, the next time you look up at the night sky, you might remind yourself of this. We are surrounded by these patterns. We are inside one. Our local patch of the Milky Way was carved out by ancient cataclysms. And some of those beautiful stars you see, those stellar nurseries, are plastered along the walls of the supernova-blasted cavity, a cavity that might just be connected to the rest of the galaxy through invisible interstellar tunnels. Wow! We have spent our time together, immersed in the aftermath of supernova. We've explored the ghost they left behind. But imagine for a moment. Imagine you're looking out your window, perhaps on a night just like this one, when a singular bright light suddenly flares into existence in the sky above you. This new, dazzling star is as luminous as the full moon, perhaps even brighter. It is a terrible, beautiful new jewel in the night, and it is even visible during the day. If you can see this light, you might already be in trouble, because that unexpected star is now flooding the upper atmosphere of the Earth with a catastrophic dose of gamma radiation and X-rays. This invisible storm of high-energy light is, at this very moment, stripping away our precious ozone layer, exposing all life on the surface to the full, unfiltered, deadly radiation of our own sun. And on its way, jettisoned out at 10,000, maybe 40,000 kilometers per second, is a cataclysmic wave of stellar matter and debris. It is the dying roar of that exploding star, venting billions of tons of burning, radioactive mass at us, ready to sweep across our planet's surface in a tidal wave of fire. This is a supernova, or at least, it's one interpretation of what we might see if one were to occur too close to home. We've just explored the history of our bubble, but it begs a far more urgent question. How likely is it for this to actually happen? What constitutes near us on a cosmic scale? How close would a supernova blast have to be before life on Earth would be truly threatened? What might we, on Earth, actually experience? And what stars near us right now have the potential to detonate in this way? I'm Alex McCone, and you're with Cosmic Whispers. Join me as we move from the past to the future and discuss an event that could be an Armageddon in our lifetimes, or could be nothing more than a pretty twinkle in the sky. Let's start with the good news. First, let's all take a calm, deep breath. Supernova in our own galaxy are not that common. While astronomers observe hundreds of supernovae every single year, those are almost all in other galaxies. This is mostly a reflection of just how many galaxies there are in the observable universe. Closer to home, though, within our own Milky Way, we estimate that a supernova only occurs about 2 or 3 times every century. This means that the odds of one going off tomorrow are not that high, but they're not impossible. Rare is not the same as never, and according to our planet's own geological and archaeological record, the Earth has likely been hit by the fallout from a supernova before, during the course of its 4.5 billion year existence. For starters, as we've just discussed, we exist in the local hot bubble, a region carved out by supernova that happened 10 to 20 million years ago. Our planet was certainly around for that. And as we also discussed, scientists have found evidence of another, more recent detonation, the one that happened about 2.5 million years ago, which rained down that iron 60 onto our ocean floors. That supernova, thankfully, happened far enough away to be harmless to us. But this might not always have been the case. There are some scientists who believe that the extinction of the woolly mammoths was not caused by climate change or human hunters, but by a massive piece of debris from a more recent supernova, which crashed into the planet about 13,000 years ago. The impact site in question is rich in magnetic spherules and radioactive potassium-40, a substance known to be found in supernova ejecta. It's a smoking gun, found in the exact era when most mammoths went extinct. Even before that, mammoth tusks from 34,000 years ago had been found containing tiny impact craters. When analyzed, these craters were found to be from grains of slightly radioactive iron that had been traveling at a staggering 10,000 kilometers per second. If you recall, that was one of the potential speeds of supernova explosions. One can only imagine what that must have been like for the mammoths in question. A rain of high-velocity radioactive shrapnel from the sky. An astute observer, however, might be able to note an important fact from all this. Evidently, if life began on Earth about 3.7 billion years ago, and we have faced the fallout from multiple supernova explosions in just the last 20 million years, and life as well still largely ticking along, my condolences to the mammoths, then supernova as a whole can't be quite as universally destructive as my opening introduction made them out to be. And that is largely true, although it is, of course, a question of proximity. A firework is a wonder from a mile away. It's a different story if it detonates in your hand. A nuclear explosion is survivable from 1,000 kilometers away. It is not survivable if it detonates on your coffee table. And when it comes to supernova, it turns out that the universe has relatively large coffee tables. To understand the scale of these explosions, the kill zone, and the threat, it's necessary to understand the forces involved. And that means we need to understand a little better about how supernova happen. It turns out there are two main paths a star can take to get to that explosive grand finale. Although, in each case, it has to be the right kind of star. The first path results in what is called a Type 1, a supernova. This path usually involves a white dwarf, the small, incredibly dense, burnt-out core of a star like our Sun that is in a binary system with another, healthier star. This white dwarf, being so dense, has immense gravity, and it begins to siphon matter away from its neighboring star, like a cosmic vampire. This path is not fully understood, but it's thought that a white dwarf, which is a giant core of mostly carbon, like a giant superdiamond, is normally held in a fine, delicate balance. On one side, you have the crushing, relentless force of gravity, trying to collapse the star even further. On the other side, you have a quantum mechanical force called electron degeneracy pressure. This is simply a rule that says atoms, and specifically their electrons, really object to being squashed too close together. They will resist being pushed denser than a certain point. This pressure is the only thing holding the white dwarf up. But in that binary system, as the white dwarf is absorbing more and more matter from its neighbor, its mass climbs. It gets heavier and heavier and heavier. Eventually, it reaches a critical point, a specific mass known as the Chandrasekhar limit, where gravity overwhelms electron degeneracy pressure. The entire house of cards collapses at once. The spring shatters. In that instant, the carbon in the core ignites in a runaway fusion reaction. Within a few seconds, most of the star undergoes fusion, forming into heavier elements and releasing a truly mind-boggling amount of energy. How much energy? Around 1/4 of a rotorillion joules. That's a 1 followed by 45 zeros. All of this energy is released in just a few seconds. Naturally, the star cannot handle this. It ejects its entire contents out in all directions, sending a shockwave of matter traveling at 6% the speed of light and unleashing a flood of mostly gamma radiation. The brightness of this event is staggering. It can be 5 billion times brighter than our sun, and it will burn that brightly for a few weeks, until the ejecta has expanded and dissipated its initial incredible energy. The second type of supernova, a Type 2, is similar in its violence, but different in its cause. Instead of involving a white dwarf, it involves a massive star, at least 5 times more massive than our Sun at the very end of its lifetime. These stars are still burning brightly, and rather than just electron degeneracy pressure, it is the active, ongoing heat and pressure of nuclear fusion in their cores that keeps the star in balance, pushing outwards against gravity's inward pull. But just like in a Type 1a, that balance eventually collapses. This time, it's because the star simply runs out of fuel. A massive star fuses lighter elements into heavier ones, hydrogen to helium, helium to carbon, and so on until it creates iron. Iron cannot be fused to create energy. It is the end of the line. When the core runs out of fuel, the scaffolding of fusion energy that was pushing outwards is suddenly kicked away. Electron degeneracy pressure on its own can't possibly cope with the immense weight of these giant stars. The collapse is immediate, and it is catastrophic. The outer layers of the star come crashing down onto the core rebound, and the star explodes in a Type 2 supernova. The only difference is that while some of a massive star will remain often collapsing down into an ultra-dense neutron star, or even a black hole, a Type 1, a white dwarf, usually vanishes completely, leaving nothing behind. Either way, the scale of material and energy released by a supernova is vast. So vast that, unsurprisingly, anything immediately next to it is not going to last long. This is an energy powerful enough to rip apart another star. A planet is going to have no chance if it's in the immediate vicinity. Our own Sun, thankfully, will never go supernova. It is simply not massive enough. It is not a white dwarf in a binary system siphoning matter, and it is not a massive giant destined to collapse. Our star is a gentle, stable G-type main sequence star. Its end, billions of years from now, will be a quiet, dignified sigh as it puffs its outer layers away to become a planetary nebula, not a galactic roar. But other stars are not so kind. But if such a star were to detonate, if it wasn't so kind, the consequences would be almost beyond comprehension. For a planet caught in the immediate vicinity, the end would be swift. There is a very good chance that the Earth, if it were in that inner circle, would be either partially or completely vaporized. Its rocky exterior, its oceans, its entire crust, would reach a boiling point, subjected to temperatures 15 times hotter than the surface of our own Sun. In the weeks following the supernova's initial flash, the planet itself would be scoured, its very substance whisked away by the expanding shell of the star's remains. What is surprising, however, is how quickly this first, most devastating wave of annihilation would dissipate with distance. Indeed, vaporization, as terrifying as it is realistically not the largest threat a supernova poses to the galaxy at large. In 2011, experts from the University of Cambridge calculated the effects. They determined that even for planets orbiting their star at a distance of 15 billion kilometers, that is about 100 times the distance between our Sun and the Earth, they would likely remain structurally intact. They wouldn't be boiled, but they wouldn't be safe. Instead, they would simply be unmoored. With their parent star now a remnant, its gravitational pull gone, these planets would be sent flying, cast out as orphan worlds, destined to wander the cold, dark void of interstellar space forever. Of course, any hypothetical ecosystem on such a planet would have far more immediate problems to worry about. Without the light and warmth of their star, things would get very cold very quickly. And this is the key. Even if the crust of a planet itself remained intact, that doesn't mean that life on that planet would be sustainable. Let's ignore for a moment the sheer blinding light of a supernova, an event that can for a few weeks outshine the brightness of an entire galaxy, a light that would cause permanent blindness for anyone on the planet's surface who happened to see it. The real killer is invisible. The greatest threat is the high-energy radiation, the flood of gamma rays and X-rays that precedes the physical shockwave. Even if this radiation didn't affect us directly, here on the surface, it would be catastrophic for our atmosphere. This wave of energy would slam into the upper atmosphere, altering its chemical composition. It would, in effect, completely negate our planet's ozone layer. Without the ozone layer, our shield would be gone. The Earth would be exposed to the full, unfiltered, and deadly radiation of our own sun. The consequences would be a global-scale sterilization. We would face mass extinctions, massive increases in radiation poisoning, and the complete collapse of the food chain, beginning with the death of phytoplankton in the oceans. This is the true kill zone. Scientists have placed this threshold of devastation at roughly 25 light-years. Any star that goes supernova within that 25 light-year bubble poses a direct, existential threat to life on Earth. Beyond that 25 light-year mark, the fury of a supernova begins to calm. Distance, even in a galaxy, is a powerful shield. The radiation and energy, expanding in all directions, wears itself out, dissipating across the sheer volume of space. Though, admittedly, there is that lingering mystery of the mammoths. If that asteroid did come from a supernova, as that theory suggests, it would have come from an explosion that was perhaps 250 light-years away. If that theory holds any water at all, it was likely just a case of extraordinarily bad luck, a single stray piece of shrapnel from a battle fought long ago and far away. Generally speaking, we wouldn't expect to notice any significant damage from a supernova at that distance. Its radiation levels wouldn't be high enough to trigger mass extinctions. By the time you get to 500 light-years, we would hardly notice the event at all, other than perhaps the sudden and beautiful appearance of a new bright star in our night sky, which leaves one very important and very practical question. Within our local neighborhood, are there any candidates we need to worry about? Are there any stars within that 25 light-year kill zone, or even within the 300 light-year concern zone, that are poised to explode? Thankfully, astronomers are fairly confident that the answer is no. Massive stars, the kind that become Type II supernova, are very noticeable. They are the giants of the night sky, and we have a good census of them. The only two famous candidates in our general vicinity that are at risk of going supernova any time, geologically, soon are Betelgeuse, the shoulder of Orion, and Antares, the heart of the Scorpion. Both of those are more than 400 light-years away, far, far outside the kill zone. White dwarfs, the Type Ia candidates, are a little trickier. Thanks to their diminished brightness, their burnt-out state, they have been conventionally very hard to spot. This made it much harder to predict whether we might be at risk from one we simply hadn't seen. However, this is where our modern instruments have given us a profound sense of peace. In 2013, the European Space Agency's GS Space Observatory released a massive packet of information in its ongoing effort to map the stars. This data allowed scientists to identify and chart 13,000 white dwarf stars within 326 light-years of us. It's a large number. But in spite of this, scientists remain confident that none of these are scheduled to explode anytime soon. And in astronomical terms, soon means within the next few 100,000 years. None of them are in the process of siphoning matter in a way that would lead to an imminent detonation. Speaking of Betelgeuse, there are some scientists who predict that this red giant might detonate much sooner than that, perhaps within the next few decades. This research works under the assumption that Betelgeuse has a much larger radius than previously predicted. But if it is true, it might mean that we, you and I, would get to see a local supernova within our lifetimes. But even then, according to our best models, we would have nothing to worry about. The physical shock wave, the blast of matter traveling out from Betelgeuse, would take a very long time to get to us. And even once it arrived, it would be traveling with less force than the gentle, constant push of our own solar wind. In other words, it wouldn't even be our planet's magnetosphere or atmosphere that kept us safe. The protective sheath of our sun's own heliosphere, the bubble our sun creates around our solar system, would be more than enough to keep such a distant supernova at bay. So there you have it. While supernovae are, perhaps, some of the largest and most terrifying explosions in the universe, it seems that through some fortunate stroke of cosmic luck, our patch of the galaxy has nothing really to fear from them. The odds of us being hit, even by the fallout from neighboring stars like Betelgeuse that are scheduled to go supernova, are incredibly, infinitesimally small. True, our Earth has plenty of its own cataclysms. Floods, earthquakes, and hurricanes can bring devastation to a community in a heartbeat. And space is, and always will be, a dangerous place. But it is a comfort, isn't it? It's nice to know that of all the things we have to worry about, we can probably cross planetary annihilation from an exploding star off our list. We are safe, it seems, from the fire. But our journey in the last episode, our exploration of the local hot bubble, revealed a different kind of challenge. Not all of our universe is visible. Not all of its secrets are written in light we can see. Our galaxy is filled with dust. Vast cosmic clouds of dust and gas that act like a veil, a fog cloaking entire regions from our view. What if I told you that, hidden behind that veil, more than 1.5 billion unseen objects, from entire distant galaxies and newborn stars to some of the oldest, most ancient stars in our entire galaxy, are sitting just out of our reach? That's a little frustrating to think about, isn't it? Until now, that is. Because thanks to the European Southern Observatory's, ESO, Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift that veil. For the first time in human history, we have a truly comprehensive infrared map of the Milky Way. It is a map that pierces through that obscuring fog of space to reveal an unprecedented, breathtaking view of our galaxy and all that lies within and beyond. Welcome back to Cosmic Whispers. I'm Alex McCone. Join me today as we appreciate how this first-of-its-kind map was made, and take a look at some of the stunning images that reveal previously unknown stars and structures across our galaxy. In September 2024, the VISTA project published the largest and most detailed infrared survey of the Milky Way ever undertaken. This was not a quick snapshot. This map was the culmination of a 13-year period of painstaking work, from 2010 to 2023. Across 140 nights of dedicated observation, this project captured around 200,000 images and generated 500 terabytes of data. To put that in perspective, that is the same amount of data as it would take to stream a 4,000 video non-stop for nearly 3 years straight. VISTA is part of ESO's Paranal Observatory, located high in the desert mountains of Chile. Its main focus is to map large areas of the sky. Using VISTA's powerful infrared camera, known as VIRCAM, the team was able to peer through the dust and gas that permeates our galaxy and uncover some of the Milky Way's most hidden places. Traditional telescopes, and our own eyes, allow us to view space in visible wavelengths, the rainbow of light that ranges between about 380 to 700 nanometers. But VISTA isn't like a traditional telescope. Instead of relying on visible light, VISTA operates at near-infrared wavelengths, between 900 and 1,200 nanometers. This longer wavelength light is not as easily scattered or absorbed by cosmic dust. It sails right through. This allows VISTA to detect otherwise invisible objects, stars completely obscured by dust clouds, and cold, dim objects like brown dwarfs, often called failed stars, which simply don't emit enough visible light to be seen with a traditional telescope. To get an idea of the difference, take a look at these two images of the Lobster Nebula. One is taken in visible light. We see the beautiful glowing gas, but the center is thick with dark, obscuring dust. Now, here is the same region as seen by VISTA. In the infrared, the dust that obscures our field of view seems to disappear. It becomes transparent. And suddenly, we are looking at hundreds of thousands, perhaps even millions, of previously invisible stars. This map was created through a project called Vista Variables in the Via Lactea, or VVV. Via Lactea being the Latin name for the Milky Way. It also included a companion project, the VV Extended Survey, or VVVX. The data collected from these two companion projects is what makes up the Vista Infrared Survey, and it has already been a revolution. This data has led to the publication of more than 300 scientific articles. Unlike other recent space maps, this is one of the most detailed and comprehensive ever made. It is the first infrared survey to cover nearly 80% of the Milky Way's total luminous mass. It provides the largest infrared catalog ever made of our galaxy's central region. It allows astronomers to study our galaxy in finer detail than ever before, giving us an accurate 3D view of the inner regions of the Milky Way that were, for all of human history, hidden by dust. The survey covers an area of the sky equivalent to 8,600 full moons, and it contains about 10 times more objects than any previously published infrared map. Our Milky Way consists of a central bulge, a dense, bright, puffed-up collection of stars, and a flat disk with two spiral arms wrapping from the ends. This image shows the area of our galaxy that was mapped. The red squares mark the central regions, the bulge, which were observed by the original VV survey, and then re-observed by the extended VVX survey. The other colors show areas of the disk observed by the extended survey. You can see that these surveys focused right on the central plane of our galaxy, spanning part of the disk, and most importantly, that dense, mysterious nuclear bulge. So what has Vista revealed? The Argentinian astrophysicist who led the survey project, Dante Minetti, put it simply: we've made so many discoveries. We have changed the view of our galaxy forever. And as much as I would love to talk about all of them, it's probably best to stick to some of the highlights. For decades, the central bulge of our galaxy was a mystery. We knew it was there, a bright, dense concentration of stars at the center of the Milky Way, but we couldn't see into it. The prevailing theory was that this bulge was an ancient feature of our galaxy's past. It was a fossil, a collection of exclusively old stars, formed billions of years ago, perhaps when our galaxy first came together, and that it formed separately from the stellar disk we inhabit. Vista, by piercing that veil of dust, has shown us that things are not so black and white. One of the first and most profound discoveries came in 2016. For the first time, a type of ancient star known as an RR Lyrae variable was discovered in the very center of the Milky Way. RR Lyrae stars are special. They are very old, over 10 billion years old, and they are typically found in globular clusters, those tightly packed, ancient spheres of stars that orbit in the outer regions of our galaxy's halo. Finding them in the dense, chaotic center was a huge surprise. The team, led by Dante Minetti and Rodrigo Andres Ramos, found 12 of these RR Lyrae stars. This suggests that they might be the surviving remnants of an ancient globular cluster, or clusters that were torn apart by the galaxy's gravity and whose stars were absorbed into the central bulge. This finding provides powerful evidence that might help astronomers decide between the two competing theories of how nuclear bulges form. While some scientists think the bulge forms gradually over time as gas is funneled inwards, others say it forms early in the galaxy's evolution, when multiple smaller galaxies and primordial globular clusters violently collide and merge. Finding these ancient stars, these fossils, right in the heart of the galaxy, lends strong support to that first theory, that the bulging center of the Milky Way likely grew at least in part through the merging of these ancient primordial clusters. It's a discovery that not only hints at our own galaxy's violent beginnings, but also offers compelling evidence for how galactic bulges might form in other similar galaxies across the cosmos. But this is where the story gets beautifully complicated. As Vista continued to stare at the galactic center, it found something else, something that contradicted the ancient bulge theory. A team of astronomers and data scientists, looking toward the galactic center, found 655 candidate stars of a different type, Cepheid variables. They sorted these into two classes and found that 35 of these 655 stars were classical Cepheids. This was a shocking discovery. Why? Because unlike RI Lyrae stars, classical Cepheids are young. Recording their pulsation periods, the team revealed that all 35 of these Cepheids were less than 100 million years old. Some of them may be as young as 25 million years old. To put that in context, our own sun is about 4.5 billion years old. The youngest of these stars has only been around for 0.6% of our sun's lifespan. By mapping these 35 young, classical Cepheids, the team was able to trace a completely new feature in the Milky Way, a feature that had been buried behind those thick clouds of dust. They found a thin disk of young stars that stretches right across the galactic bulge. This finding completely rewrites our understanding of the bulge. It implies that there has been continuous star formation along the midplane of the galaxy, not just for billions of years, but for the past 100 million years. The bulge is not a fossil. It is a living, breathing, evolving part of our galaxy, still creating new stars today. We used to think the galactic bulge was an ancient, static relic. This finding reveals that the formation of newer stars within the bulge could be a natural, ongoing progression of our galaxy's evolution. These Cepheid variable stars are more than just clocks. They are also one of the most powerful tools in astronomy. You can think of them as a kind of cosmic yardstick. Cepheids are a type of bright star that is unstable. They physically brighten and fade, pulsating over a period of a few days or a few months. The first variable star of this type ever identified was Omicron Ceti, also known as Mira. It had been described as a nova, or new star, until 1638, when the astronomer Johannes Vesalides Holwarda observed it getting brighter and dimmer in a cycle that lasted 11 months. What makes them a yardstick is a special relationship. The longer a Cepheid's pulsation period, the time it takes to go from bright to dim and back, the brighter its true, absolute brightness is. If you know its pulsation period, you can infer its absolute brightness. And if you compare that absolute brightness to its apparent brightness, the amount of light that actually reaches use here on Earth, you have a precise measure of how distant that star is. VI's power to find these stars is perhaps best shown in one of its earliest discoveries. In 2015, VISTA turned its attention to the star formation region of Messier 20, also known as the Trifid Nebula, which lies about 9,000 light-years from Earth. Viewed in visible light, we see a beautiful nebula, glowing pink from ionized hydrogen, surrounded by a blue haze of scattered light from young, hot stars. But the cloud of gas and dust is thick, obscuring the star-filled space behind it. Now, look at the second image, taken by VISTA. Peering beyond the clouds reveals a whole swarm of new stars. This image didn't just allow us to see through the Trifid Nebula. By sheer chance, it revealed objects on the far side of our galaxy that had never been seen before. To their surprise, astronomers identified two faint reddened objects as Cepheid variable stars. While they appear in the image to be just behind the edge of the nebula, in reality, they are 7 times farther away than the nebula that once helped to block them from our view. They are the only Cepheids we have identified so far in this location, which lies beyond the central bulge on the far side of our galaxy. With reference points like these, we can begin to build up a real 3D picture of the true scale of our galaxy. And VISTA just kept finding things. In addition to these ancient and young stars, VISTA was able to find whole new clusters of stars. Did you know that there were only 158 known globular clusters in the Milky Way before these new surveys? These ancient, rare objects are the bedrock of our galaxy. For the VISTA survey to identify two more of these rare stellar objects, named VVCLO01 and VVVCLO02, is a significant accomplishment. In this visible light image, a known globular cluster, UKS1, can be seen on the right as a hazy red splotch. It was the dimmest known globular cluster until these new discoveries. Now, compare this same patch of sky in VISTA's infrared light. Suddenly, we see what we've been missing. Much fainter than UKS1, we can make out a second globular cluster in the upper left, VVVCL001. These discoveries bring exciting possibilities. It could just be an illusion of perspective, but scientists have wondered whether VVVCL001 is gravitationally bound to UKS1. If this is the case, they would be the Milky Way's first ever known binary globular cluster pair. We've found binary clusters in other galaxies, like the Large Magellanic Cloud, but scientists think it might be when these gravitationally bound clusters finally collide that we get the most massive globular clusters in the universe, like the famous Omega Centauri. Studying a binary cluster right here in our own galaxy could produce amazing new insights into this process. It's all speculation at the moment, but it's an exciting thought. Beyond the rare globular clusters, the VISTA survey also identified a multitude of other types of clusters. At least 96 new open clusters, or galactic clusters, have been found. These typically contain fewer, younger stars and are much more common. Like everything else, they were hidden by dust, but VISTA's 4.1-meter infrared telescope has lifted the curtain. Take a look at just a few of these stunning images we now have. One of these open clusters, VVCLO03, is the first of its kind to be discovered on the far side of the galaxy, 15,000 light-years beyond the Milky Way center. The sheer scale of this survey is staggering, covering a vast region of the sky and mapping more than 1.5 billion objects. This data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way. And that's just the tip of the iceberg. This survey will serve as a foundation for future telescopes and observations, which will, we hope, be able to expand on VISTA's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map ever made of the Milky Way structure, one that has unveiled hidden wonders previously beyond our reach, and scientists are already using it. Combined with the recent work from ESA's Gaia mission, Invisible Light, it is an incredibly exciting time to be an astronomer. We can expect a flurry of new insights about our own galaxy and the universe as a whole. VISTA's infrared observations have unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries and broadened our understanding of our galaxy's formation. Looking at the sky through different wavelengths has truly brought about a new era of galactic exploration. And I, for one, can't wait to see what else they're going to uncover. It's a lot to take in, isn't it? The scale of these structures, the violence of supernova, the immense, intricate map of our galaxy. It can feel abstract. Some of you may remember the first video I ever did on this channel, a simple thought experiment. How big is our solar system if the sun was the size of a football? Today, I'd like to do that again, but this time, to truly feel the scale we've been talking about, I want to scale it down even more. Imagine for a moment that our sun is not a football. Imagine it is a single 1 millimeter grain of sand. Hold that in your mind. A single tiny speck. Now, let's take a walk. We'll start with that 1 millimeter grain of sand, our sun. The closest planet to our sun is, of course, Mercury. On this scale, Mercury would be just 4 centimeters away, about the width of your thumb. The next closest planet is Venus. It is 8 centimeters away. And the next one is us, Earth. Our world is 10 centimeters away from that 1 millimeter grain of sand. Then we have Mars, which is 16 centimeters away. The next object we'll mention is Ceres, the largest object in the asteroid belt. This dwarf planet is 30 centimeters away. We're not even half a meter from our sun, and we're already past the inner planets. The next one is Jupiter, the king. Jupiter is 56 centimeters away. We're getting farther away now. Saturn, with its beautiful rings, is 1 meter and 3 centimeters away. You'd have to take a step. Coming to the first of the ice giants, we find Uranus. It is a massive 2 meters and 6 centimeters away. You'd have to take another, larger step. The last true planet in our solar system is Neptune. That is 3 meters and 24 centimeters away. It's across the room. And then we have Pluto, which, on this scale, is 4 meters and 22 centimeters from our single grain of sand. Our entire solar system, all the planets we know and love, fits inside a very large room. At this point, you may be wondering, what about the closest star, Alpha Centauri? Well, on this same scale, where our sun is a 1 millimeter grain of sand, and Pluto is just 4.2 meters away to find the next grain of sand, the star Alpha Centauri, you would have to follow me. You would have to leave this room. You'd walk out your front door. You'd walk down your street, out of your neighborhood, across your town. You would have to walk for 30 kilometers. That's over 18 miles. An 18-mile gap of empty space to get to the next closest grain of sand. That is the scale of our galactic neighborhood. And that is the scale of the void that Vista and Gaia are now mapping for us. This journey, this exploration of our cosmos, is in part made possible by all of you, and especially by all the wonderful supporters on Patreon. If you think these explorations add some educational value to the world, and if you want to help give these videos more stability than the whims of the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch every new video entirely ad-free. You'll see your name in the credits as a supporter, and you can submit questions to our team. You can sign up with the link in the description. Meanwhile, you can click the link to the playlist on your screen for more Cosmic Whispers content. Thank you for joining me on this journey. I'll see you next time.